So in this video, I want to look at a different example of figuring out what the equations of motion are for a rotating and translating system. This is a system that's going to involve constraints, and I want to sort of show you a couple of ways to go about it. One is the more complicated way, and one is the easier way. It's kind of one of those classic ones that often gets done in textbooks, so my apologies. But the sort of idea is that you have a yo-yo that's sitting on the ground, and you've got a string that's coming off of the yo-yo one way or the other, and you're pulling on that string, right? And you're interested in knowing how is the yo-yo actually going to move? What are the equations of motion that describe the evolution of this system as you sort of pull on the string? What happens if I pull hard? What happens if I pull lightly? What happens as the coefficient of friction maybe here changes on the ground? What happens as I change the radius of this? Those are the kinds of things that you might hypothetically be interested in figuring out. So to do that, I'm going to mostly look at the sort of free body diagram and coordinate systems and how we actually go about figuring out what the equations of motion are. I'm not going to really talk about keyframes on this and interactions very much. So let's first think about just a free body diagram for this. So if I go to a free body diagram, I'm cutting out the yo-yo from the rest of the universe. So one of the forces that I clearly have is some tension force that I'm applying to it. And this is a force that I presumably know. It's however hard I'm pulling. And the other thing is that at this point on the ground, there's going to be an interaction between the ground and the yo-yo. Clearly, gravity is going to be pulling down on the yo-yo, and there's going to be a normal force that's going to be up to the extent that the yo-yo is going to be confined to be on this flat surface. Those two things are going to offset. But there's also going to be a frictional force on the ground. And if you imagine sort of pulling this across the ground, that frictional force is going to be wanting to resist your pulling it across the ground. So I'm going to say the frictional force is in that direction. Okay. I don't know what that frictional force is because I'm going to assume that this is rolling motion. So this is actually going to be a static frictional force. It'll be whatever it needs to be in order to support the motion. Okay. So that's my free body diagram, and I've identified what the different interactions are that are important. Let's think about what the state variables are for this system. Well, pretty clearly it only can move in the x direction. So one sort of quantity of interest might be the position of the center of mass, which I'll call x. So I could say my position vector for the center of mass is simply x in the i-hat direction. But it's also going to be rotating, right? And so you can imagine saying that at any given time, if I sort of imagine putting a dot on the yo-yo, there's some angle theta that's the yo-yo's current angular state. Okay? And if you actually think about this, if you've actually got this yo-yo constrained to roll without slipping, there's a relationship between theta and x. In particular, it's going to be the case that x is going to be simply whatever the diameter of the yo-yo is, which I'll call r sub y for radius of the yo-yo. Right? So this is, I'll call r sub y, times theta with a negative sign in front of it. And why is there a negative sign? Well, if you imagine the yo-yo sort of here with zero angle, as it rolls forward, right, the angle is going to become more and more negative, right? It's going to, so moving in the positive x direction implies a negative change in the angle. Okay, so at this point we've got a definition for what the position vector of the center mass is. We've got these two state variables, x and theta, and we also have x dot and theta dot as state variables. So now we should probably be able to go on and try to write down what the sort of expressions are for the forces here, and also what the expressions are for conservation, right? So what are the forces? Well, the forces are fairly straightforward. There's a known force, T, in the i-hat direction, and an unknown force, F, in the i-hat direction, and that's in the negative i-hat direction, given the way I've drawn the picture. All right. If I think about momentum, right, the momentum of this object is going to be fairly straightforward to write. It's simply going to be the mass of the yo-yo times x dot in the i-hat direction. I can also think about torques and angular momentum. And to do that, there are a couple of options. One option that seems fairly obvious is to take torques about the center of mass. So let's take the center of mass option first. If I take my torques about the center of mass, I can see that I'm going to have one torque that's going to be a negative torque, because it tends to make things move clockwise. That's going to be simply F times the radius of the wheel. And I'll say that's in the k-hat direction. And then also this tension is also going to tend to move things in the clockwise direction, or the negative torque in the negative k-hat direction. So it'll be minus a tension times r sub a, where r sub a is that axle radius. Also in the k-hat direction. So those are what my torques are about the center of mass. Now, it's often the case that the center of mass is a handy place to calculate torques about. It's not always the case that the center of mass is a handy place to calculate the torques about. There's actually a better choice in this particular problem, and often with rolling motion this is true, that a good point to calculate the torques about is actually not the center of mass, but instead the contact point. And the reason why the contact point is a good point for calculating the torques is that you can see that that actually takes the frictional torque out of it, which is an unknown torque, and allows you to say that the only torque acting on the system is this tension, right? So if I take my torque about the contact point, I get different answers, right? And about the contact point, my torque is again going to be negative, right? So it's going to be negative t, but the distance that I'm interested in, or the radius from the origin to the point where the force is applied, is actually going to be the radius of the wheel plus the radius of the axle. Okay. So I have two options for torques. And notice that I also, once I've identified those two options for torques, I also need to figure out my angular momentum in those two different options. So my angular momentum about the center of mass is fairly straightforward, right? It's just going to be the moment of inertia about the center of mass times theta dot in the k-hat direction. On the other hand, my angular momentum about the pivot point, now since this pivot point is not actually moving, I can think about that angular momentum as being purely rotational, but it will be rotational where I have to use the moment of inertia of an object of a sort of disk that's rotating about the edge. Another way of doing that same thing is to have it actually use the sort of r cross p plus I center of mass times theta dot, which is actually the same thing as saying radius of the wheel times the velocity of the wheel times the mass of the wheel, right? Mass times velocity here, so this is going to be m times nrw squared times theta dot plus ICOM times theta dot, or I center of mass plus m times rw squared times theta dot. So in fact, what we've done here is we've just used the parallel axis theorem to come up with what the moment of inertia is, or actually we sort of derive the parallel axis theorem to come up with the moment of inertia is for the wheel about this point as opposed to about this point, because this r cross p term gives you this m times the distance from one axis to the other squared. Okay, so at this point we have expressions for the forces, we have expressions for an expression for the angular momentum, we have an expression for the torques in two different choices of origin, and expressions for the angular momentum in two different choices of origin. So now we want to actually figure out the equations of motion. And I think I'll go to a clean sheet for that. So let's do the hard option first, and then do the easy option. The hard option is where we simply sort of blindly apply summation of forces. It tells you the time rate of change of momentum. Summation of torques tells you the time rate of change of angular momentum. So if we do that, what we get is m times x double dot, right? This is the time rate of change of the momentum, is equal to plus t in the I hat direction minus f in the I hat direction. And since everything's in the I hat direction, I'm simply going to leave that. So that's one of my differential equations. Similarly, the summation of torques, right, this is if I take the time rate of change of the angular momentum is the summation of torques, well, the time rate of change of the angular momentum in this case is simply going to be moment of inertia about the center of mass times theta double dot, and that's going to be equal to minus T times R sub A minus F times R sub W. Okay? So this all, this doesn't look bad, right? You've got one equation here for x double dot, one equation here for theta double dot. So we have two equations, but we've got a problem because we actually have three unknowns, right? We've got friction that's unknown, and ultimately we want to find x double dot and theta double dot. So we actually need a third equation here. Our third equation is our constraint, which is to say that x is equal to minus r times theta, or another way of saying that is x double dot. If that's the case, it must be the case that x double dot is equal to minus r times theta double dot. So at this point, I can substitute this back in, say here, in order to solve for theta double dot. Okay. So that's one sort of approach for this. I won't go through the algebra. You can go through the algebra yourself. It's not super involved to do, but every time I do it, I make a mistake, so I'll spare you that mistake in this video. Now, the easy option is actually the one that says, let's choose an intelligent origin for calculating our torques, in particular an origin that eliminates friction from the picture. And so if you remember when we calculated the torques about the contact point, our torque didn't have friction in it, right? And our angular momentum didn't have friction in it. So if we take it about the contact point, then what do we have? Well, the torque about the contact point is the tension in the string times Rw plus R axle with a negative sign, right? Because it's tending to rotate. If we look back at this, that torque is tending to rotate this whole wheel clockwise. And that's equal to the time rate of change of the angular momentum. Well, the angular momentum is the moment of inertia about the center of mass plus m times the radius of the wheel squared times theta dot, right? In other words, we get I center mass plus mRw squared times theta double dot is equal to minus T times Rw plus Ra. Or solving, theta double dot is equal to minus T times Rw plus Ra divided by moment of inertia about the center of mass plus m times Rw squared. Okay. So if you actually look at this, you can see we never actually had to figure out what x double dot is, and we could apply this constraint to find x double dot. We never had to figure out what the friction is because our calculations actually were chosen about an origin we didn't need to know the friction. So in some ways, this is a much easier approach because instead of dealing with three equations and three unknowns, you're actually dealing with one equation and one unknown. Now, it's obviously not always the case that you can do this, but when you've got constraints, this is kind of like choosing your coordinate system to minimize the number of state variables you have. By the same token, choosing your origin to minimize the number of equations or the number of unknown constraint forces that you have can also be a pretty powerful approach. And I'll note that if you go ahead and you do the math over here, you'll get the same answer. One last comment on this is it's worth just looking at the expression for a second and thinking about what it means. One of the things that it says is that when you increase the radius of the axle, that you increase what the rate of change of theta double dot is, right? And that makes sense because increasing the radius of the axle actually increases the amount of torque that that force is applying. The other thing that we can see is that when you actually increase the mass of the wheel, that you're actually going to both decrease the acceleration of the wheel both through this term and through this term. Both of these terms are going to depend on the mass, so mass shows up in the denominator as we might expect.